Let's talk about simplifying some radicals. When you're simplifying radicals, there's a few different approaches that you can take. So I'm going to talk about a few different methods here. First, we'll do some square roots like these ones, and then on the next slide, I'm going to do some cube roots and fourth roots. So square roots we can simplify by identifying perfect square factors within each of our radicands. We have a property of radicals that says if you have two things underneath your radical that you're multiplying, what we can do is we can take that radical and we can split it up as the product of each of those factors separately. So if I'm able to find a perfect square factor within one of these, I can go ahead and just essentially pull it out and square root it by itself. So that's what I'll do first for square root of 108. So square root of 108, I'll go ahead and start by factoring. I can divide that by 36 and 3. Now, the reason I chose 36 was because I know that 36 is a perfect square. So I can say that this is actually the square root of 36 times 3, and then I can split it up using that property that I just showed above as square root of 36 times the square root of 3. Square root of 36 we know is 6, so I just have 6 times the square root of 3, and that's as far as we can go because 3 is prime. We can't factor that any further, let alone find any perfect squares inside of it. So this would be simplified form of square root of 108. If we did it that same way for square root of 150, I would see that there's a perfect square of 25 in 150. So this would be 25 times 6. And then I can split up that 25 and the 6 into two separate radicals. Square root of 25 is 5 times square root of 6. So this will just be 5 times the square root of 6. And I know I'm done because if I try and factor 6, the only two factors that are helpful here are the 2 and the 3. And neither of them are a perfect square, so I can't simplify that any further. So this just stays as 5 square root 6. And then for number 3, I already have that perfect square of 49 in my radical, so I'll just split up that one, and then I'll keep the square root of x cubed in its own radical. Square root of 49 is 7 times the square root of x cubed. Now we need to do the same thing on the x cubed, which is a little bit weird, but if we go back to the last couple, when we're finding perfect squares, we're basically finding something that can be raised to the power of 2. So for example, when I look at the 25, the reason 25 is a perfect square is because it's actually 5 squared. So then when I square root it, that's where I got just 5, because the square rooting undid that power of 2. And then same thing for 36. Here when I had my 36, the reason it's a perfect square is because it is 6 to the power of 2. And then when I square rooted it, I got just 6. So really, I want to rewrite my x to the third as something to the power of 2. So what I can do is split it up into x squared times that third x. So x cubed is x times x times x. That's what I have here. I'm just doing x times x in one group and then times x to get that third x. So then I can split up my radicand into two separate radicals. And like we said, if we're square rooting something squared, the radical and that exponent undo each other. So these two pretty much undo each other, or the square root of x squared is just x, and then I'm multiplying by 7 and I'm multiplying by the square root of x. And that's as far as we can go because underneath that radical, I only have one x. I can't write that as a perfect square, so we leave it like this. Now, if you're not a fan of that, maybe you're not super comfortable with your perfect squares, then we can take another method to simplify each of these. So let me go ahead and erase, and I will show you the second method. Okay, method number 2 says, let's factor and then make groups according to the index of your radical. The index is a little invisible number that's right here inside the check mark. And if it's not showing, then it's implied that it's a 2, meaning in order for anything to come out of the radical, there needs to be 2 of them. And that's why we're looking for perfect squares, because squares are groups of 2. So for example, this 108, we already know factors into 36 times 3. And if I keep factoring, I'll see that there are groups of 2. My 36, for example, factors into 6 times 6. And that is a group of 2. Because they paired up in a group that matches the index that I'm given, I can take out a 6 to represent the two sixes inside. So outside my radical, I will have 1 6, and that represents the group of sixes inside. So these are now done. I've used them because I've pulled them out. But inside, I still have that 1 3 that didn't pair up with anything. So the 3 stays inside. So I would have 6 square root 3 as my simplified radical. For 150, I could factor this into maybe 15 times 10. Maybe you're not comfortable with 25 times 6, but you see 15 times 10. So let's start there. Then I break down my 15 into 3 times 5 and my 10 into 2 times 5. And again, this is a square root because there's nothing written in that index spot, which means that there is an implied 2. So I need to make groups of 2 in order for anything to come out of the radical. So when I look at my factors, I see that there are 2 5s. So that means that I can take out a single 5 to represent the pair of 5s that I just grouped. So I take out a 5 that represents this whole group. And then inside my square root, I still have the 3 and the 2 that didn't pair with anything. And I just keep them multiplied together. So I would have 5 times the square root of 6. Number 3. When I factor, I know 49 is 7 times 7. And then my x's, if you want, you could write them as x times x times x. And again, this is a square root, so I'm looking for groups of 2. I'm going to go ahead and circle this time 2 groups of 2. So that tells me I can take out a 7 and an x from the radical. Both of those groups have now been used, so the only thing left inside my radical is an x. So this whole thing simplifies to 7x times the square root of x. So this method is really helpful, especially as you start dealing with indexes that are not 2, maybe a cube root or a fourth root. As your powers get higher, oftentimes they're a little bit harder to recognize. So for example, let's take a look at these. You could still separate out your powers, but you have to make sure that whatever power you're separating out matches the index that you're given. So in this case, this first one, the index that I'm working with is a 3. So I need to separate out perfect cubes. If I decided to use our first method where we have the product underneath, and I can split that up into the product of 2 radicals, then I want to make sure I'm separating out a cube. So I have the cube root of 16, and I happen to know that 16 divides by 8, and 8 is a perfect cube. So the cube root of 16 could be written as the cube root of 8 times 2, which is the cube root of 8 times the cube root of 2, and the cube root of 8 is 2. So this becomes 2 times the cube root of 2, and that would be as far as you can go with that one. But if you're not comfortable with cube roots, then you're going to need another method. So let me go ahead and erase this, and we will go through it using the other method from the last slide. So 16 factors into 4 times 4. 4 breaks down into 2 times 2 and 2 times 2. You can kind of cross out the other factors that you're not using if that's helpful to you. And I'm going to go through and circle groups of 3 identical factors. And again, I want 3 because I have a cube root. So when I look at my factors, I see that there are 3 2's, which means I can bring out a single 2 outside the radical, but then inside the radical is whatever's left. And that would be this fourth 2 that didn't group up. So just like I had the first time I did it, I have 2 times the cube root of 2. So that's going to be how I do the next couple. Number 2, now I'm looking for groups of 4 because I have a fourth root. Breaking down my 324, I at least know it's even, so let me start there. I've got 2 times 162. I can keep breaking it down until I hit my primes. And I will definitely go back and cross out anything that's irrelevant here because I have a lot going on. So I have 2 2's and 4 3's. Since I'm looking for groups of 4, I can circle these 4 3's and take out a single 3 to represent this entire group. But then inside my fourth root, I still have a 2 and another 2. I multiply those together and I would have 3 times the fourth root of 4 as my simplified radical. Okay, last one. I'm going to go ahead and factor, and I am looking for groups of 3. 162 we actually just had as part of our last one, but 162 factors into 81 times 2, and then I'll just keep breaking it down from there. So on the outside, if I'm looking for groups of 3, because we have a cube root, I'm going to have a 3, but then on the inside, I will have a 2 and another 3. Now when we look at our x's, my x's are going to break down into x times x times x times x. There are 4 of them. And in order to come out of the radical, I only need 3. So I can circle a group of 3 of the x's, but one of them is going to stay inside. So on the outside of my radical, I can have a 3 and an x, and then those numbers have all been used. Inside the radical, I keep my cube root. I have a 2, a 3, and an x. So my final simplified form is 3x times the third root of 6x. So that's a few examples of simplifying some radicals. I hope that helped. Thanks so much for watching, and I will see you next time. Bye.